Okay, so welcome back to the final session of today's program. So we have two talks now. We start with Devvrat Tiwari from IIT Jodhpur, and he is going to talk about quantum thermoelectric circuits, a universal approach. So Devvrat, over to you.
Thank you. Am I audible? So, hi, thank you very much, first of all, for giving me opportunity to present here and arranging such a fantastic conference. So, I'm a fifth year PhD student at IIT Jodhpur, and I will present basically, so my work is related to quantum thermodynamics, and I'm going to present a universal approach on quantum thermoelectric devices. So, first I will talk like these works started from these papers like by Casati, Ling and Wang in PRL from in 2004, where they developed a thermal circuit for quantum thermal diode. Then in 2017, they Ordonez Minanja and others used spin like qubits and connected to hot and cold baths and basically observed rectification kind of behavior where this can be observed as a forward and reverse bias current basically, which is reminiscent of a quantum classical diode. And so moving on, there have been studies on various other quantum thermal versions of classical electrical devices, one of which is the thermal transistor, which is again studied by this group. And here basically there were 3 qubits, and as you can see, this base current, when it is modulated a very little, then we can get a very high gain in this basically collector and emitter currents, which is represented by L and R here. And on a similar footing, this thermal transistor was also studied by the group of N-Gupta, where in the base frequency they provided flow-K driving basically. And recently, an interesting circuit has appeared, which is a quantum thermal version of the Wheatstone bridge. So if you arrange your qubits like this, which is in a similar symmetry as we can see for this Wheatstone bridge. So this group tried to find out what could be the balance conditions such that the current between this and this qubit goes to 0. And we will also discuss these conditions and how we were able to basically make this condition more robust. So, so here in this particular paper, we are asking one question like, what could be the universal laws that can be applicable in such a circuit, or for classical electrical circuits, you get laws like Kirchhoff's current laws, voltage laws, and there is also Ohm's law. So using those laws, you can study basically any type of classical circuit. So whether a thermal version of those circuits or those laws can be found. So, and also like in these previous circuits, the current was basically like coming from this bath and this bath, and the current was calculated using the rate of flux, heat flux through the whole system at once. So like if we want to calculate particularly the current between this and this qubit and this and this qubit, this and this qubit, it was not there. So first of all, we redefined the this formulation of quantum thermal current. And to do this, let's say we take any qubit and it is connected to n number of other qubits, and it is also connected to a bosonic bath, and similar to for this qubit and this qubit. And a general Hamiltonian for this can be written like this, where this is the interaction Hamiltonian between these L and K qubits. Now, the dynamics, we use the weak coupling and Born-Markov approximation between this qubit and the bath, and in general, the dynamics is given by this master equation, which is GKSL master equation. And so, to find out the thermal current, first we find out the energy and take the time derivative of this. Now, you see this term will go to 0 since we are taking this Hamiltonian is constant during this evolution, and only this term will be contributing to the change in the rate of change in the energy. So which can also be seen as the rate of change in the heat. Now, if we, and this we are doing for the mth qubit. Now, if you just use this equation and expand after some algebraic manipulations, we come out to this thing where we get two terms. So the first term can be seen as a thermal current between, let's say, qubits L and M. So the terminology is like if the heat current is going from qubit L to qubit M, then this is the contribution. And if the heat current is going from the bath capital M to qubit M, then this is the contribution. And which can be seen here. And fortunately, a similar kind of formula was also derived by a group from Tanimura's group on heat current, where they studied strong coupling regime also. So, but anyway, here one interesting feature we can see right away that if we put this state to be the steady state of the system, this left hand side goes to 0, right? And this we call, let's say if the qubit M we consider as a node, then at this node the contribution of heat current from all the other qubits as well as from the bosonic bath comes out to be 0, which is kind of a quantum thermal version of Kirchhoff's current law. And further, we can do further manipulations, and we can find that if this quantum thermal current measured at qubit K or measured at qubit J has a very unique or very interesting relationship where both are related via their transition frequencies. And interestingly, if you remember, this is a kind of transformer-like relationship between these two qubits where the currents are basically related to the number of turns of the coil at the iron rod. Now, these laws we now try to implement on a basic circuit, let's say 2-qubit quantum thermal circuit. And so we find out analytically the steady state of the system, and then we calculate the currents. And as we thought, and as we let's say this current from this to this and this to this were equal and opposite, and that came out to be 0. And similarly, from this to this and this to this, basically taking qubit 2 as a node was also equal and opposite. And from this and this equation, we can directly see that this the currents J21 and J12 are related like this. Now, further moving on, we also want to develop like what will be the thermal potential. So to do so in this particular circuit also, we find out the reduced steady state of this qubit and compare it with the particularly given Gibbs state of the system. And we find out, let's say this is the effective temperature, if we can call it effective temperature of qubit 1, and similarly an expression for qubit 2 can also be found. So, and how this effective temperature connects to the heat current? This is connected via this relationship, which can be seen from this graph. So it is like at lower temperatures, this is following this particular expression, and at higher temperatures, this comes out to be this constant like expression. And also, so the potential difference between this bath and qubit, we call it as T1 minus TA, where T1 is the effective temperature we got here, and TA, if here it is, in this particular example, it is 0. That is how it is. And moving on, if we do that similar analysis in a 3-qubit quantum thermal circuit, then so these are the components of the steady state for the 3-qubit system, and we have reduced it for, let's say, to obtain the thermal current at or effective temperature at qubit 1. And in a similar way for T2 and T3 can also be found. So an interesting thing is if that way we find out the effective temperatures and we define the potentials between these and these qubits like this, like 1 is T1 minus 0, 2 1 is T2 minus T1, 3 minus 2, 1 minus 3 like that. It's very trivial to find out that this relationship will also hold. And interestingly, this is a version of Kirchhoff's voltage law. So, and again, we develop basically what is the relationship between this current and the potential difference between these two qubits. So this comes out to be like this, where f is a very intricate, very non-trivial kind of functions. I have avoided it here, but it is there in the paper, you can see. So, and also we tested all the previous laws on thermal currents here, and we found out that these are perfectly satisfied, at least numerically. Now, as we discussed this Wheatstone bridge thing earlier, now since we have an expression for the thermal current between each qubits, here we explicitly calculate the thermal current, this J34, and find out the conditions where this can go to 0. And this balance conditions comes out to be this thing, so that this J23, which is the interaction strength between this and this, and interaction strength between this 2 and 4, if those two are equal and those two are equal, mind you, these J23 and J13 need not be equal, they can be anything different from each other. And in this scenario, we found out that this current is always 0, and we checked it, we compared it with the previous condition obtained in this paper. So at higher temperatures, as you can see in this inset plot, this is moving up a slightly a little bit, and whereas in our case, this is always going to 0. So that is kind of a more robust balance condition which is obtained here. And next, we also propose a kind of novel quantum circuit. So it was a fun kind of doing these things. So let's say if you have these number of qubits, 1 to n, and they are connected to corresponding bosonic baths, this Roman numerics 1 to n, and then they are also interacting with the single qubit. We are calling it alpha here, and it is interacting with the bosonic bath at 0 temperature, or it can be any other temperature as well. But for simplicity, we have taken 0. So if you find out individually using the rules and on thermal currents that we developed previously, it can be easily found out that these thermal currents, which is coming from bath Roman 1 to 1, qubit 1, Roman 2 to qubit 2, and n to n, they are related to this heat current, which is coming from bath A to alpha, and which is like this. So, and if you just put all these factors to be equal, like omega alpha to be omega 1 equal to omega 1 or equal to omega 2 and up to n, then you find this relationship, which is very much similar or exactly similar to kind of the relationship that we obtain in a operational amplifier, DC operational amplifiers adder circuit. So, this was a very interesting result in this scenario, and we also want to study the relationship between these currents and the effective temperatures on these qubits. So these Tj are the temperatures T1, T2, Tn, and these Tk are the temperatures of qubit 1 to n, and they are related to each other by this relationship, where curl Jk is this heat current, but from bath 1 to qubit 1. And after, if we do some simplifications, then we can find a very nice kind of relationship where this Tx is the effective temperature of all these qubits that is related to the temperature of the bath via this relation, where omega alpha and T alpha are the effective temperatures of the qubit alpha and corresponding transition frequency. And also, let's say if we want to develop a relationship for the voltage also, where the sum of this thermal potential between this and this and this and this should be equal to this thing. So this we did numerically, and for this set of parameters, and of course after these conditions, mind you, this is a nice exponent which came out. This is a golden ratio which came out there. So in this condition, we found out numerically that in high temperature regime, this condition satisfies with higher accuracy. So that is all, and we also discussed the previously studied circuits, which was thermal diode, and in using our formalism, let's say the 2 qubit thermal circuit I showed, there also this thermal diode can be studied using that model also, and we also see a similar kind of relationship that previously was obtained, and this transition relationship is also obtained like this. So where these are the amplification factors we get in the emitter and collector currents. So that is it. We conclude. We studied a general framework that can be applied to any kind of quantum thermal circuits in this way. And we also developed this Kirchhoff-like voltage and current laws. And we also made novel circuits as made the existing circuits robust. And further, so the open questions that we asked that what happens or these laws, whether these laws are applicable when the couplings is little stronger, and then what are other novel quantum thermal circuits that can be implemented using these laws, and what are the experimentations that can be done using these rules. And so basically we want to test the rules using some experimental devices, and what are the realization of these thermal devices. So that is all, and thank you.
Okay, thank you, Devvrat, for the nice talk. Questions for Devvrat? Okay, so actually, I have a question because from some classical settings, you know that if I see this kind of structure, let's say I have two bars, and then I have between two bars, I have some chain of oscillators. Okay, if I take this like active bars, so there are some kind of universalities in the correlation of the currents. So do you see something like that here? So if you like try to compute the correlation of the currents, so have you ever done this thing or
no? We did not do that, but definitely, I mean, that can be checked. And if you share some references for that, I will share. Surely we can do something, because
I can.
we have some analytical results also. So there we can find out whether these correlations are there between the heat currents that we have studied. Surely that can. Yeah. Sure.
Okay, so with this, any other question? If not, so let's thank Devvrat once again.